I had intended to deliver this talk at the American Geophysical Union Winter 2024 event. It turned out I wasn't able to travel to Washington, D.C. and deliver the talk in person, so I've decided to record the talk in the form of this video. So the title of my talk is The Right to Reproducible Execution. My name is Jim Colliander. I serve as the partnerships lead for the International Interactive Computing Collaboration. I'm a professor on leave from the University of British Columbia, and I served previously on the NASA TOPS community panel. I'm grateful to my colleagues at 2I2C and others in the communities that I serve for their wisdom and guidance that have heavily influenced this presentation. People have recognized for a long time that humans want knowledge, and there's discourse that suggests that there ought to be a right to knowledge. And there's a long literature, a long historical discussion about why there might be, or there needs to be, a human right to knowledge. Some of the reasons are baked into the individual. Part of the way that an individual can grow involves accessing and processing information, developing knowledge. Another is that society advances collectively when people have access to knowledge. And then in the context of democracies, citizens participating in decision-making need access to knowledge. This is recognized in things like the United Nations Declaration, and in other sources. India has a right to education. So there's a deep commitment on society that there ought to be a right to knowledge. But the right to knowledge is aspirational. How can we grant people knowledge? What does it mean to implement this right? And the ways that the right to knowledge, this grand plan, have been implemented over time have evolved. Societies have adapted to technological innovations and changed the ways that they deliver on this right to knowledge. So some examples of that evolution. In the era of the printing press, books could be created. That was great. But at that time, books were extremely expensive. So how do people get access to the knowledge inside of books? We need other implementation innovations. The technology of the printing press and the outputs of that technology, the books, those alone were not enough to facilitate access to this knowledge. So inventions like libraries and public libraries in particular were built to provide sort of social structures, social infrastructure to complement the technological advances. And these libraries and the books that came out of the printing press facilitated the right to read, a less ambitious but still very important subset of the right to knowledge. Advances in teaching of the older generation to the younger generation eventually created an evolving education system. Harvard College became Harvard University after Johns Hopkins University was built in the model of the University of Berlin, now called Humboldt University. So through these processes, there emerged the right to education, a kind of subset to this more ambitious, more abstract right to knowledge. With the era of the network interconnecting computers all over the world, there emerged a bunch of content, the World Wide Web. All of this content on the web then provided new ways for people to access knowledge. And while there is still a big digital divide between those that have access and don't have access to the internet, there has emerged a right to internet access. And we're now in an era of cloud computing, where the static content that's rendered on the World Wide Web can be complemented with new capacity to execute. One can run code and provide reproducible experiences, and this is an exciting era that I want to talk about today. So the organization that I'm working with, 2I2C, has developed another version of this ambitious right to knowledge that we call the right to replicate, which is our promise to the communities that we serve that we will deliver infrastructure for them to do research that is leveraging the commercial cloud, but in such a way that is cloud vendor agnostic and built with open source tools. This ensures that the stack, the technologies that are used for scientific communication, are owned by no one and are more like a digital public good. In this talk, I want to speak about another version of this right to knowledge, which I'm calling the right to reproducible execution. And this is emerging from this idea that we have the executable web, a new opportunity that has been facilitated by the cloud computing era. So a scientist may have a really great idea, and she wants to share that idea fully rendered with an interested collaborator or a reader. Or a reader is interested in learning more about how a scientist has developed a really interesting idea. So how do we facilitate this transition of an idea above one person's head and render that idea fully above the other person's head, thereby propagating knowledge from one person to the other? How do we make this sharing possible? Well, ideas in the era of the executable web are quite complicated. These ideas may involve a blending of software, data, and hardware with curated choices made by the creator of the idea. And all of these curated choices need to be propagated with the content, with the description of the idea, with the narrative around the idea, in order to fully render the idea above the creator's head into the consumer or reader's head. So how do we propagate content, hardware, and software from one person to the other in this cloud computing era? This is another example of that complexity with an image extracted from a paper by Shel Gentiman and collaborators. So a user is trying to understand, say, the Earth system, and is doing so by looking at data that's coming off of, say, NASA satellites. And she's analyzing the data that's coming off of those NASA satellites using hardware that might be on a commercial cloud entity like Google Cloud or on Amazon Web Services or Microsoft Azure. And she's using tools like Python or NumPy or Dask to analyze all of that information using a curated collection of software and hardware. And she makes a breakthrough. Now she wants to share that breakthrough with others, but all of this complication around the software and hardware and data makes it a challenge to share the result with others without finding a nice way to combine all of this how the discovery took place information with the what discovery took place description that might appear in a paper. If we can send information from one scientist to one reader, there's also the possibility that we can broadcast these ideas together with the data, software, and hardware complexity from one to many. And this era of cloud computing comes with it an ambitious idea that I learned this phrasing from an excellent essay by David Donahoe from earlier this year called frictionless reproducibility. We want readers to be able to reproduce with as little friction as possible all of the code and execution and data necessary to fully understand an idea that a scientist has made. So how can we facilitate frictionless reproducibility by taking advantage of this cloud era? Well, one way to do that is to use BinderHub. So BinderHub is a project that's developed by the open source ecosystem adjacent to Project Jupyter. And BinderHub is a cloud service that allows users to share reproducible, interactive computing environments from code repositories. So Binder provides a way to bundle up a description of hardware, a description of software, and content that takes advantage of that software and hardware and allows a reader, by just clicking a link, to experience the fully executable stories that a content creator has made for sharing. And Binder and its and Binder links and NB Git puller links that are happening associated with JupyterHub are all examples that demonstrate the technical capacity to use the cloud to facilitate this reproducible execution. And we can probably improve. I think we will definitely improve on stitching together all of these ideas into a more robust and easily used protocol for sharing content with reproducible execution. An instantiation of BinderHub that was made by the BinderHub team is called MyBinder. And this is a free-to-use BinderHub service that anyone in the world can use. Anyone can generate a MyBinder link, and this MyBinder link will execute when anyone in the world clicks on that link. So there is a publicly accessible cloud service that enables rendering of executable content. Unfortunately, this service doesn't scale as effectively as we would like because of challenges around covering cloud costs to make this service work. Right now, the MyBinder service is covered through the Binder Hub Federation through these three generous contributors, CurveNote, Geesis Notebooks, and OVH Cloud, are enabling reproducible execution for creators that want to share and readers who want to interact with the content that these creators share. This talk is really about exploring ideas to try to find ways to sustainably scale cloud cost coverage to make Binder a publicly accessible, universally accessible, and scalable higher performance service. The technical achievement of Binder Hub and MyBinder is fabulous. There are opportunities, I believe, to go beyond what was achieved with MyBinder and make this service more universally accessible. So how can we make Binder a public good? I want to explore some ideas that might allow for us to expand beyond the MyBinder scope using some business innovation exploration ideas. So MyBinder Access right now allows anyone to generate executable links. And once those links are created, those links can be clicked by anyone and anyone will receive the execution. That is an ambitious, beautiful proof of concept that MyBinder is scalable, but there is a problem that the cloud costs associated with execution right now are not sustainably recoverable. So how can we find a way to make this MyBinder style access more generally available? And I want to throw out some ideas associated with maybe playing around with access to generate business improvement opportunities. So maybe we can design around who can share, who can generate these shareable links. Instead of making it so that anyone can generate links, suppose we change it so that my team can generate links that execute. I'm really wanting others to be able to render with execution my work, but I don't necessarily want to pay for some other team's executable costs. So I'm happy to maybe pay for people to look at my stuff, and I'll put money down to help my stuff get rendered, but I don't want to pay for someone else have their content rendered on my dime. Maybe I would like to make my stuff available, but I can't afford it. So if people who really want to see my stuff could subscribe to my feed and pay to cover the costs of their execution, maybe that would work. These ways of controlling who has the power to generate links is one way to possibly generate new revenue to come into the Binder ecosystem. We can also design around who can execute. Instead of making it so that anyone can execute public repos, maybe we can change it so that the only content that will execute is content in an allow list managed by my team. So for example, maybe the National Science Foundation would pay for execution of repos that emerge from NSF-funded research. Maybe not. Maybe Howard Hughes Medical Institute would pay for content generated by HHMI principal investigators to execute, but they don't want to pay for execution of content that's generated by NASA. So maybe there's a way where we can play around with the content execution allow list to also create funding opportunities that lead to more investment in the Binder ecosystem. So with funding from NASA through an HPOS award, my colleagues at 2I2C and some of the folks in the communities that we serve are experimenting with these access constraints as pathways to possibly generate a more vibrant and sustainable revenue flow into the Binder ecosystem. So we've launched Binder.OpenSci, a Binder service that provides medium compute that is publicly accessible, much like MyBinder, to anyone in the world, but we're restricting the content that will render with execution to those repositories that are inside an allow list. So the idea here is define an allow list of NASA adjacent content and then use Binder.OpenSci to render with execution this NASA adjacent content, but don't render with execution content that is not appearing on the allow list. And we're starting to experiment with ways to manage this allow list. We've also launched a big binder service, which provides bigger compute than can sustainably be delivered right now, given the cloud costs. And the only people that can execute content using the big binder are people that are appearing inside of an allow list of authorized users. So how do we manage who's an authorized user, who's NASA adjacent and therefore should be accessing or have access to the big binder service? These are questions that we're beginning to explore as precursors to potentially rolling out eventually a sustainable revenue-backed service with big compute for authorized users and medium compute for the public, but will only launch content in an allow list. So I'm very grateful to NASA for funding these experiments. If you are affiliated with NASA in some way and wish to access the big binder, I invite you to send us an email. Send an email to binder-requests@2i2c.org, and we'll get you set up so that you can access the big binder for your reproducible execution needs. So just a couple comments on some demos that are available. So my colleagues at 2i2c have taken some really interesting content that's been built by communities that we serve and set up a Mist Markdown or a Mist engine site located at 2i2c.org/demo gallery. These demo sites are taking advantage of the medium compute OpenSci binder, and there are 3 examples that I want to highlight. So work on TOPS-T, that's a NASA-funded project related to Science Corps, has done some analysis on climate risk, taking advantage of NASA Earth data. And there's a beautiful demonstration that shows how NASA data and compute can be explored with execution. Jessica Scheich has just been awarded the Open Science Recognition Prize by AGU for her open science contributions and notably her leadership of the IcePix project. So IcePix is a collection of Python tools for analyzing and working with NASA's IceSat-2 data stream for understanding Earth's ice. And there's a nice development of a tutorial on IcePix rendered with improved interactivity by my colleagues at 2i2c. And we've also developed a nice radar cookbook that was originally built by Project Pythia, a project that has spun out of the Pangeo group. So this Project Pythia radar cookbook is also rendered as an interactive Mist site. Each of these 3 sites are backed with a Thebe engine so that there is inline execution using the OpenSci binder as a headless Jupyter Hub execution. And they can also, all of them can also be launched into a Jupyter Hub interaction by clicking on the little rocket engine launcher from each of these sites. So the 4th place, your example, I invite you to play with binder.opensci and learn from the way these Mist sites are set up. So start to share your content with reproducible execution. And I thank you very much for listening to me and watching this video.